I was having some technical difficulties, shall we say, because that's the easiest way to do it, is that I was having some technical difficulties trying to get onto the website that I wanted to show you to help you with the photoelectric effect. So I have now solved that because I'm going to show you from my iPad because it's better. And remember, what we were talking about on Tuesday is the fact that with the photoelectric effect, the point is that light comes onto a metal, hits the metal, and then ejects the electrons off the metal, okay? And it's one of the things we use to prove or to show that light is a particle, because if it was a wave, it wouldn't happen. So I'm going to show you the animation that I wanted to show you, and hopefully it'll make sense. And I'm just going to talk you through it, okay? And you should be able to hopefully see my screen in a second. There we go. So if we look here, so what we have here, all right, we have a cathode tube. Don't worry about what the tube is, okay, where you see the little green thing moving, okay? Don't worry about that. On the left-hand side, we have sodium, okay? So that's just one of the metals. It's a default metal, okay? And so it's a default metal that we put there. Don't worry about the power supply. That's irrelevant at this point. Look at the ammeter. All right. And what I want you to see is I'm going to change the frequency of light. Okay. So if you watch, I'm going to increase the wavelength. All right. So I'm going to take it to the right towards the red section. Okay, and as I increase the wavelength, okay, the frequency gets smaller, and then eventually we don't get anything. Don't worry about the minus noughts and stuff. That's not the point. But you can see that there's no more blue dots moving from side to side. That means I've reached a wavelength and a frequency of light that isn't high enough for electrons to get off. If I make it brighter, which is what the photon density is talking about, which is in the bottom left-hand corner. So now I make it brighter, which is meaning I've got lots and lots of more light coming. It doesn't matter how bright I make it, I still am not going to get any electrons, okay? Because it's not about brightness. I said that to you on Tuesday. It's about frequency. So even if I go back down here and I make it very dim light, okay, it's the dimmest this will let me go. So it's dim light. And I take my light back into the green section. I can still get a current. It'll be a small current, but I can still get a current, okay, as the electrons move from one side to the other. So I can still get a current. I'm getting the electrons to move off. Now, if I increase the frequency of the light, what I want you to see is that now the electrons are moving faster, so I'm getting a bigger current. Okay, well, I should be. All right. And I can keep getting a current, and then we end up in black, so we're not going to worry about that. But as soon as I get to the yellow end of the spectrum, nothing will come out. If I increase the photon density, when I get to the blue side, I get a much bigger current, okay? Now watch what happens. If I increase the photon density, in other words, I increase the intensity of the light, I make it brighter, I get more electrons coming off. That means the current increases, okay? So that's with sodium. That's just an example with sodium. If I change the metal, so let's change the metal to platinum, okay? So now I'm going to put platinum there instead. Now the blue doesn't get me any light. So when that was sodium, I could get a current. Now I'm not getting a current, which means we're not going to worry about that, which means we haven't reached the threshold frequency. Electra, just stick with me. It's what we were talking about. It'll make sense in a second, I hope, Electra. If I change the frequency, so I'm making it higher frequency. Actually, it's not going to matter here. What this is telling me, so no lights, I can't get electrons to come off. That's what the little yellow things are, is, and I won't get anything there, is platinum. We don't use platinum in photoelectric cells. So let's go to something else, okay, a better metal. Let's use gold. Okay, so now I've changed it to gold. I did change it to gold. Gold. Okay, it doesn't want to go to gold. There we go. Now it's at gold. Let's see if we can get any electrons to come off this one. Okay. No. Electrons don't want to come off that one either. So let's go to another one that we can actually see something off. Let's do copper. Okay. Copper. Oh, also doesn't want to do anything. So let's not do that. Let's do calcium. Okay. Let's do calcium. So you can see with calcium, I can get electrons to move off. Okay. So the light has sufficient energy that when it hits the calcium metal, those light particles, which are like the little spacey, rectangular, fishy type things that are pushed going onto the calcium, as they hit, they transferring energy to the calcium. Okay, that energy then allows the electrons to move off. So if I increase the frequency of the light, what you can see, it's not as obvious with calcium, but the electrons actually start to move faster. I can increase the current. But watch, if I start making the frequency smaller, okay, eventually, now they start to go very slowly, okay? We'll talk about how that works in a second. So now I've now gone below my threshold frequency. So the frequency of the light, no matter how bright I make it, will not allow electrons to move off. Okay? Whereas if I reach that threshold, which is about there, okay, even if I make it very dim, the electrons will still come off. All right, so that's not the brightness of the light that's important. It's the frequency of the light. In grade 10, you learned that the frequency of light gives us the energy because you did photons, okay? You did photons. So this hopefully helps a little bit, okay? Make it very bright, and we just get lights coming off at a very slow rate though. Okay, they're not getting faster, there's just more of them. All right, and every single metal has its own threshold frequency. Okay, every single metal has that. And some we can get to those thresholds, some we can't. You just saw with the platinum and the gold and all the rest of it that we can't get there. If we now change to nickel, okay, let's not do that. No, I just want to see one that I'm actually going to get. There we go. So now I've got potassium. Potassium's threshold is smaller than the copper was. So watch. Still getting, I'm going into the green section. Okay. More into the green. Getting slower. I'm going to get there quite soon. Oops. So we keep going. I'm trying to go slowly so I can actually get it exactly there. Okay, so I've gone beyond, I've got smaller than the threshold. So no, doesn't matter how bright I make that light, no electrons are going to come off. So we won't get a current from it. Okay, when it's at a span where we've gone beyond the threshold, like there, if I make it bright, I just get a lot of electrons coming off. Okay, when I make it dim, hearing a yes, somebody's microphone went on. Do you want to ask a question? No? Somebody just forgot? Are we all good? All right, I'm going to take that as a silent yes, much to my horror, because Electra, I'm hoping you're feeling a little less lost, but I'm not sure. Okay, so let's go back here. On Tuesday when I saw you, remember we spoke about the zinc and the electrons. Okay, great. Thank you, Electra. This is what I was just trying to show you, this with other metals other than zinc. Okay, zinc very specifically uses ultraviolet radiation, and that you do need to know. It's the only metal you need to know has to use ultraviolet because it's the one we use in the experiments. And the color of light depends on the metal. Savannah, color has to do with frequency of the light, okay, and the wavelength, whereas brightness has to do with the amplitude of the wave. Okay, so color and brightness are two different things, absolutely. All right, color is red, blue, green, purple. Brightness is how bright that color is, like how much. I mean, it's the same at home when sometimes you have some light bulbs that are very bright, some light bulbs that are dim. It's a frequency. It's not frequency, it's amplitude. Okay, it's about the amplitude of the wave. So threshold frequency. So I was using that term just now. Okay, threshold frequency is also called the cut-off frequency, and it's the minimum frequency of radiation. Radiation, you're welcome, Savannah, is the term we give for electromagnetic radiation. We're really talking about light, and we're talking about light between infrared and ultraviolet. Okay, that's what we're talking about. So minimum frequency at which electrons will be ejected from the surface of a metal. Please be careful here, because, and for me, it's one of those things again where I'm like, really, are we going to be that pedantic? But apparently we are. They really want the term surface of a metal. They really, really, really want that term. All right, they don't just say from a metal, but it's from the surface. So this isn't something that penetrates like with the sun. It really is the surface electrons, okay, that are now being used. And it's electrons that get ejected, so now they come out. Tamarin, yeah, I'm saying it wrong. Sorry, sweetie. What I said about zinc and ultraviolet light is zinc is the only metal that you need to know that you will only get electrons coming off with ultraviolet. Okay, so you need to know ultraviolet works with zinc. You don't need to know, like we saw with the copper, or we start with the sodium, that it's green light that allows it to come off. Okay, it's just the zinc and the ultraviolet. Okay, so zinc actually has a very high threshold frequency. Okay, so you need light of quite a high threshold frequency to, I'm sorry, you can hear my cat. She has decided that now it's time to say hello. All right, so next part of this, okay? Every metal has a specific threshold frequency. So that's what we've got here. Sodium's is 5.5. Zinc is 1 times 10 to the 15. Platinum is 1,4. You do not know. I'll answer your question now, Electra. You do not need to know these values, okay? Electra, I actually don't know what other metals will only have ultraviolet as their threshold frequency. Okay, I really don't know because it's not something I'm required to know. Even when it comes to using this to set up, I will get there eventually, photoelectric cells, photovoltaic cells, like your solar panels. Trust me, those scientists have books where everything is just written in it, and they have tables where they can go look those things up. Okay. Gabby, are the ejected electrons that, yes? Who was mamming me?
Or sodium, zinc, and platinum.
No, you don't need to know the actual values. Okay, I think it's Eden. No, you don't need to know the values. This is just an example for you to see that they have different thresholds. Okay. You happy with that, Eden?
Yeah.
Okay.
Thank you.
Gabby, you're welcome. You're asking, are the ejected electrons the electrons? They are lost in a sense, but we allow them to go through a circuit, so they'll go back to the metal. They go in through a circuit and then they go back to the metal. So they are sort of lost, but we don't ever talk about them as being lost. Okay. Yeah, they get transferred. We can live with that. Yeah. Okay. So Electra, you're saying, you also said light intensity doesn't change the electrons that come off the metals, and frequency does. But do we say the light changes the speed? Okay, I'm getting to that, Electra. Okay, because intensity changes the number of electrons, frequency changes the speed. Okay, so intensity changes the number, frequency changes the speed. But we'll get there when I get to the equation. Okay, it'll make a lot more sense once we get to the equation and we can put all of it together. All right, so now, when a photon of light interacts with the electron, it transfers all of its energy to the electron. You can think of it as an elastic collision. Okay, it's the best way to think about it. You can think of it as an elastic collision. The photon has a certain amount of energy, and I'm just going to draw it here and then rub it off in a second. So the photon comes along, which we always draw like that. But if the photon's a particle, the photon has a certain amount of energy. It hits the electron. Okay, so it hits the electron. There's a collision. What happens? All right, we'll call it kinetic. The photon now stops. Just go with it. Okay, so now the photon won't move, and the electron will move off. Okay, all that energy gets transferred to that. Okay, so it transfers all its energy to the electron. Okay, Lauren Rose, Electra asked about the intensity and the frequency. So the intensity of light, the brightness, will change the number of electrons that come off, whereas the frequency will change the speed of the electrons when they come off. The equation will make it, will help you with that. Okay, and I'm going to do it again when we look at the things that make how we can change the current. All right, so if the frequency of light, and that's incident light, is smaller than the threshold frequency, the energy that we give to, I'm sorry, I don't want that. The energy that's given to the electron is not enough for the electron to leave. Okay, so it doesn't matter that we've given the electron energy. Electrons have to have a certain amount of energy in order to leave the metal, which is why we have that threshold frequency. Okay, so if the incidence of light is below that threshold frequency, the electrons won't move, they won't leave. Okay, that threshold frequency gives us a term known as work function. Okay, the incident light, it will be a specific color. Okay, it won't be white light. It'll be a specific color, very much so. So here, when I talk about if the frequency here, this incident light, that's going to be a specific color. It won't be white light in general. Okay, we don't work with it as white light as a whole because white has all the colors. I'm hearing somebody. Who is it? Oh, Eden, yes?
Eden, would it
Yes,
be
sweetie?
visible light then?
Well, all your colors
Would
are
it
visible.
be visible light? Okay.
No. Remember with zinc, the light that we work with is ultraviolet. All right? Ultraviolet's not visible to us. We can't actually see ultraviolet. We can experience it, but we can't see it. So it's the electromagnetic radiation. We good with that? Yeah?
Yeah.
Okay. It'll get there. I promise. This is why I can't wait to see you guys face to face, honestly. So, work function. Another special term. It's the minimum energy that an electron needs in a metal to be emitted from the metal surface. Okay, so when we look at work function, you know, and we've done this in electricity, where we've said we use the terms energy, work, etc. interchangeably, and heat. Work is measured in joules, energy is measured in joules. So what we're looking at here is how much energy does an electron need in order for it to leave the surface of the metal. That energy is called the work function. Okay, and it's got a special equation. Now, you've seen an equation that looks like this before, and we'll come back to it in a second. You did this in grade 10. You did E equals HF. And in grade 10, the fact that we did the fact that light is a particle blows my mind because it's a really difficult concept. It's not an easy concept to get your mind around. But photons, which are the particles of light, that's what we call them, have a certain amount of energy, which is equals HF. When I want to know how much energy an electron needs to have, we use this equation. That little zero and that little zero are non-negotiable. You have to put them in. There are some places where if you don't put a subscript in, you won't lose marks. Here, you will absolutely lose marks if you don't put the subscripts in. All right? You will absolutely 100% lose marks. That is a guaranteed. So, WO is the work function measured in joules. Okay? H is Planck's constant. Please be careful with Planck's constant because it's joules seconds, not joules per second. Doesn't matter. You'll be given it. It's on your information sheet. Also, it's minus 34. It's tiny, 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 tiny. What that means is, yes, I'm looking at electrons, and you're going to see, because we're going to be able to calculate how fast the electrons are moving, that they're going to move at a ridiculous speed. But because they are so tiny, they actually don't need a lot of energy to move really, really fast because they're ridiculously tiny, okay? F is the threshold frequency. So in order for the electrons to move, we need a frequency of light or radiation shone on the metal that is bigger than the threshold frequency, okay? So here we have an example. They tell you to calculate the work function, WO, of potassium, which has a cut-off I'll speak English for you guys, which has a cut-off frequency. Cut-off frequency, threshold frequency, same thing. Okay? Same thing. It's just a different word for the same thing. So we want W. We know H, it's a constant. Okay, we know the frequency because they gave it to us. So the work function, the minimum amount of energy that the electrons need to leave the metal, I'll come to you now, Luca, all right, is 3,71 times 10 to the minus 19. Okay, Luca, you asked, will we always be given threshold frequency? No. But if you're not given threshold frequency, then you must be given work function, or you must be given another piece of information. Okay. Electra, I love how you like I can just see you in class with these questions because it's exactly how you ask me and I love it. Okay. What is cutoff frequency the same as? Threshold frequency. Okay. Cutoff frequency is the same as threshold frequency. Same thing. All right. Now, here's an interesting question. Suppose light of a longer wavelength is shone on the potassium. Would the photoelectric emission, in other words, would electrons be given off? Would it take place? I have a longer wavelength. What will happen to the frequency if we increase wavelength? We did this in Doppler. Someone can type it in for me. It'll decrease. Thank you, Nasir. It decreases. That means if my frequency is decreasing, thank you, Ruth. Thank you, Amy. That means my frequency is now less than the 5,6 times 10 to the 14. If it's smaller than the threshold, nothing's going to happen. So the answer there is no. The potassium has a lower frequency. No, that is just the silliest word of. Okay, that shouldn't say potassium. That should say the light. My goodness, I really should check these. Are you angry at me, Ruth? Because now there's an angry face. Light has a lower frequency, which is below the threshold frequency. Okay? So we've got the light that's been shone has a lower frequency. This is the relationship they wanted, that the frequency and the wavelength are inverse to each other. If I increase one, I decrease the other. So just be careful, all right? Because that's one of the ones where they go, oh, let's try and trick them because we can. And you know how that works. All right, so let's try and explain the photoelectric effect a little better, because we've done lots of talking now. So let's see if we can explain it a little bit. So we know light behaves as a wave, but what photoelectric effect says to us is that light is actually a particle, because there's that collision that happens that we've spoken about. So it's like a momentum collision. And we get things called photons. Now, a photon is a name given to a quantum of energy when the energy is in the form of electromagnetic radiation. It's just a very complicated way of saying that all electromagnetic radiation, from radio waves, microwaves, gamma rays, X-rays, ultraviolet, infrared, visible light, all of those which you did in grade 10, all of those forms of radiation, they come from the sun. The sun is the only one that does all of them. All right. They behave as if they are packets of energy. And those packets of energy, that's what a quantum means, behave like a particle. Okay. So they behave like they're little packets of energy and what that also means is it's quantized. So there's a minimum amount of energy that's possible. You don't need to know what that minimum is, okay? And it comes in whole numbers. But we're not worried about that. The point is that it comes in packets. It comes in discrete packets. Discrete means whole numbers of that minimum. But that photon is basically saying to us that light is a particle. If light wasn't a particle, we would not get the photoelectric effect. Light would not eject electrons from it, okay? From a metal. It's just as simple as that. Now you see energy of a photon, any photon, infrared, X-rays, whatever, okay, equals HF, where E is the energy of the photon, H is Planck's constant, and F is the frequency. It looks like the work function because the work function was W, but remember, E and W both represent a value of energy because W is work, E is energy. They're pretty much the same thing. So it doesn't matter that that's an E now, but this is general. This is for any photon of light. The equation we did just now with the work function is to know what frequency we specifically need for a specific element, okay, for a specific metal. And by the way, work function, photoelectric effect, only works with metals. Okay, it will not work with non-metals. Very, very important. Let's look at an example. So they want the energy of a photon, okay, of infrared light of frequency 2 times 10 to the 13 hertz. They're telling me what F is. They want E. Straightforward substitution. We like questions like this, okay? This one, not so bad. Now they want the energy of the photon for a visible light of wavelength 600 nanometers. You do not need to know what color of light that is. So you don't need to know whether 600 nanometers is red, green, or blue. Nasir, absolutely. Light is both a wave and a particle. That's the whole point of this. And it behaves sometimes as a wave and sometimes as a particle. It has a dual nature. It's one of those things that doesn't really know what it wants to be when it grows up. So it decides it's going to act like both because it can. Okay. So we want E equals HF. Okay. So we're looking at E equals HF, but we don't have F. We don't have F wavelength. You vaguely remember this equation. Okay. Remember, right at the beginning, I said F equals F lambda. That was our wave equation. Okay. That wave, instead of V, we're going to use C. All of electromagnetic radiation goes at the speed of light, goes at 3 times 10 to the 8. All of it. Okay, there's no exception to that. Now remember, because you're going to see it's going to get a little complicated, if I want frequency will be the speed divided by lambda. So in place of frequency, I'm going to put C over lambda. So I get E equals HC over lambda. This equation, if it'll let me write, that one will also be given to you on your information sheet. It's actually really nice. Your information sheet will go E equals HF, which is also equal to HC over lambda, which is actually really, really nice. So what that means for us is we can find the energy of a particle, whether we know wavelength or frequency. Makes life very easy for us. Straightforward substitution. And there we go. 3,32 times 10 to the minus 19 joules. And it's tiny, and it's what I expect. Please, 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 please. Nanometers can't work in nanometers, must work in meters. Very, 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 very important. Must work in meters. Okay? Now, that gets us to the activity I would like you to try, which is on page 331, question 1 and 2. It's all part of this. Yes?
I just want to ask, I don't know if I heard correctly, but do we have to convert to meters?
Always. and it's not it. Who is it? Lauren Rose. Okay, absolutely, because meters is our SI unit.
So just please remind me as how we would do that.
No, that's fine. No. I've got a feeling you aren't the only one, so I'm going to put it in the side here. Remember, it starts with milli. If it's milli, then we times by 10 to the minus 3. Then we get micro, which we times by 10 to the minus 6. Then we get nano, and we times by 10 to the minus 9. And then there's pico, where we times by 10 to the minus 12. Okay, but generally with these ones, it's going to be nanometers. So you're just going to have to do times by 10 to the minus 9. And guys, I don't need to see proper scientific notation there, hey? That can be written exactly as I've done it. Take the number, just times by 10 to the minus 9. This one, you definitely will have to do conversions. So hopefully that helped, Lauren Rose. No, what's wrong?
Yes,
I'm having
thank
someone
you,
else.
ma'am.
Yes, you're welcome, Lauren Rose. All right. So,
just repeat.
wait, there's another one.
3 times.
Hang on, wait. Okay. Mikhail, is it possible? Okay, Eden, I'm going to come back to you. Is it possible that the questions on the section... Oh, absolutely. We're not there yet, Mikhail. We're still doing the easy ones. Don't worry. Get into the hard stuff. Eden? No? I sort of got in between somebody. Yes?
Please, can you explain how you got 3 times 10 to the power of 8?
Oh, no. This is given. So, here, 3 times 10 to the 8 is a constant. C is always 3 times 10 to the 8. It's the speed of light.
Okay.
So it'll be given.
Okay, thank you.
Amy, is that what you think of these questions? You like, no, it's not. It's all right. Don't worry, Amy. When you do the activity, it'll be better. So I do want you to look at the activity. Okay. I'm not going to push on because there's another equation we're going to put in here. All right. I was hoping to finish tomorrow, but we won't. But I just need to quickly... There we go. We've got all of you. Now, some of you are starting to leave before I've even finished with my instructions. All right, grade 12s. There's a couple of things that are going to happen from here. You're going to see on sometime tomorrow in the assignment size, I'll talk aside assignment tab on Teams. You're going to see an assignment for Doppler. I'm going to explain everything about it tomorrow. It'll probably get loaded today. All right, don't even look at it. I will explain the whole thing to you tomorrow. It's a way for us to get you to practice multiple choice and to do a little bit of, are you actually on track with us? Okay, but what I would like you to try to do for me for tomorrow is activity 1, activity 3, page 331, question 1 and 2. Okay, that's definitely what I need you to do for tomorrow. But Nasir, it's not for marks. I'm not gonna, but it's there as a benchmark. All right, I'm doing it as a benchmark. We still have 2. Electra just asked the same question. It's a benchmark, guys. It's a way for you to practice. I can't count it because you're so matric. I can't add any more assessments. It's just a way for you to really see how you're doing. So you really need to try. Don't play multiple guess, please. All right, it's just to practice. That's it. All right, hopefully that makes life a little bit easier. But that's where we're going to end for today. Okay, we're done. And it's a little bit earlier, which is fine. So you've got a little bit of time. Hopefully you can get through those. Do I need to show Kaylee? That's a hard one because we're going back next week. We've juggled things around, Kaylee. So it's hard for me to say that we're behind or we've caught up. But don't worry about it. We'll get through it. All right. We've chosen during this section to do a lot of small sections rather than one big section, which I could have spent the whole time on. Okay. So don't stress about it. I'm confident we're on track. I really am. I think we're doing okay. Plus, remember, you ain't going to get much holiday after this. I don't know how much time you're going to get off before prelims. So, we're doing okay. Is it sleep time, Gabby? All right, go sleep. You can, sleep for a little bit, have a nap, and then do my homework. Okay. Do any of you need me to put up a screenshot to put on my screen the exercise? Or do you all have your books? Let's see. I can't see the conversations because it's in all sorts of things. Lauren Rose, I am going to do my absolute best for you to not come on a Saturday. Okay. Of course you did, Jared. Jared, there's going to be an assignment put onto the teams either tonight or first thing tomorrow morning. I'll talk to you tomorrow about it. Okay. Don't stress. So you can go back to sleep now, Jared. Because that's normal. Oh, I miss that face. I miss all of you. Homework for today, Xavier, it's activity 3, page 331, question 1 and 2. Gabby's already asleep. Yeah, we all good? Can I end the meeting? You all know what we're doing? Yes? Somebody's mic's on.
Oh, sorry, ma'am. My phone won't end the call.
So should I just end the meeting? Is that what you're trying to tell me? Okay, so you can go. Got it. All right. I love you all, and I will see you soon. No, Tyler, you can't have a free tomorrow, but well done for asking. Let's stop recording. I'm going to end it now, Angela.
I also want to sleep, ma'am.
Yes, go sleep. I'm going to end. Give me 2 seconds. There we go. And I've ended the meeting. Bye, Angela. Sleep nicely.
Thank you, ma'am.
You're welcome. Mine doesn't want to end the meeting either, apparently.
Bye, ma'am. Thank you.